September 1942. Lae Airfield, New Guinea. A Curtiss P-40 Warhawk sat tilted on its damaged landing gear at the edge of the jungle strip, its olive-drab paint scorched by fire, the shark-mouthed nose art still grinning despite the bullet holes that stitched across the fuselage. Japanese ground crews had recovered it after the pilot belly-landed following a dogfight over the Owen Stanley Range. The aircraft was surprisingly intact. Lieutenant Commander Masatake Okumiya, a naval aviator and technical intelligence officer, walked slowly around the American fighter, his expression unreadable. He had flown against these aircraft dozens of times over China and now here in the South Pacific. His own Zero fighters were faster in climbs, turned inside the P-40s effortlessly, and possessed superior maneuverability in every traditional measure of fighter performance. Yet, somehow, impossibly, American and Allied pilots in these crude-looking aircraft were achieving kill ratios that defied Japanese expectations. Chinese skies had belonged to the Zero until the Flying Tigers arrived with their shark-mouthed P-40s. Now, in New Guinea, the same pattern was repeating. Okumiya ordered his maintenance crews to begin detailed examination. What they discovered over the following weeks would force a complete reassessment of what made a fighter effective. The P-40 wasn't winning through superior performance in traditional metrics. It was winning through a design philosophy that prioritized survivability, structural strength, and diving speed over the nimble elegance that Japanese engineers had perfected. The Americans had built a fighter for a different kind of war, and Japanese pilots were paying the price for not understanding that difference. This is the story of what happened when Japanese engineers finally examined their enemy's fighter up close and realized that American design philosophy had outmaneuvered Japanese tactical brilliance. The Curtiss P-40 Warhawk had entered service with the United States Army Air Corps in 1940, derived from the earlier P-36 Hawk through the addition of an Allison V-1710 inline engine. It was never intended to be a technological marvel. By the time Pearl Harbor brought America into the war, the P-40 was already considered somewhat obsolete compared to newer designs like the P-38 Lightning and the forthcoming P-47 Thunderbolt and P-51 Mustang. The P-40E variant that Japanese engineers examined in New Guinea weighed approximately 8,800 pounds, fully loaded. Its Allison V-1710 39 engine produced 1,150 horsepower at 15,000 feet, adequate but unimpressive. Maximum speed was 362 miles per hour at 15,000 feet. Service ceiling was approximately 29,000 feet. Initial climb rate was 2,650 feet per minute. On paper, these specifications were inferior to the Mitsubishi A6M Zero in almost every category that mattered in traditional fighter combat. The Zero weighed just 5,313 pounds empty, almost 3,000 pounds lighter than the P-40. Its Nakajima Sakai radial engine produced only 940 horsepower. Yet the aircraft's light weight gave it exceptional performance. Maximum speed reached 331 miles per hour at 16,000 feet, slightly slower than the P-40, but not dramatically so. Where the Zero truly excelled was maneuverability and climb performance. Rate of climb exceeded 3,000 feet per minute. Service ceiling was 33,000 feet. Most critically, its turning radius was extraordinarily tight, allowing Zero pilots to outturn virtually any Allied fighter in sustained turning combat. Japanese pilots had dominated Chinese skies since 1940 using these advantages, confident that their aircraft represented the pinnacle of fighter design. But the kill ratios were wrong. Intelligence reports from China showed that American volunteer group pilots, the Flying Tigers were achieving remarkable success despite flying the supposedly inferior P-40. Between December 1941 and July 1942, the Flying Tigers claimed approximately 297 Japanese aircraft destroyed while losing only 14 P-40s in air combat. Even accounting for overclaiming, which affected all air forces, the ratios were disturbingly one-sided. In New Guinea, Royal Australian Air Force pilots flying P-40s were similarly effective. Japanese pilots reported that the Allied fighters refused to engage in turning combat, instead using slashing diving attacks that exploited speed advantages the Zero couldn't match. When Japanese fighters tried to pursue diving P-40s, the results were often catastrophic. Lieutenant Commander Okumiya had witnessed this firsthand. In June 1942, over Port Moresby, he had watched a Zero attempt to follow a diving P-40. The American fighter accelerated away effortlessly, reaching speeds that made pursuit impossible. When the Zero pilot tried to match the dive angle and speed, the aircraft's controls became increasingly stiff and unresponsive. Multiple reports documented similar incidents. Zeros experiencing severe control difficulties at high speeds, some suffering structural damage to control surfaces or wings during aggressive high-speed maneuvers. This wasn't an isolated incident. Reports from across the theater documented Zeros suffering control, stiffening, and structural problems during high-speed flight. Japanese engineers had prioritized lightweight and maneuverability, accepting structural limitations as the price of agility. The fabric-covered control surfaces, while effective at normal combat speeds, became rigid and difficult to move as airspeed increased. American engineers had made the opposite choice. The examination of the captured P-40E began with the airframe. Japanese structural engineers immediately noticed the robust construction. The fuselage was built around heavy longerons and formers, creating a structure that could withstand extraordinary loads. The wings used multi-spar construction with heavy-gauge aluminum skin, far thicker than Zero wings. One engineer measured the wing skin thickness, approximately 0.04 inches, nearly twice the thickness of Zero wing skins. He understood immediately what this meant. The P-40 could sustain dive speeds that would cause serious problems for a Zero. The trade-off was weight, but American designers had accepted that penalty in exchange for structural integrity. Japanese pilots who flew the captured P-40 in test flights reported that the aircraft could achieve very high speeds in steep dives, significantly faster than a Zero could safely handle. While exact speeds varied depending on altitude and dive angle, the P-40 consistently demonstrated superior high-speed performance. At these velocities, a Zero would be experiencing severe control stiffening and potential structural concerns. The P-40 pilot could pull out smoothly, zoom climb back to altitude, and repeat the attack. This was the boom and zoom tactic that Flying Tigers and other P-40 units used so effectively. The control surfaces revealed more American design philosophy. The ailerons were metal-covered and manually operated through a system of cables and pushrods. While they required more physical effort from the pilot than the Zero's lighter controls, they remained effective at high speeds, where the Zero's fabric-covered control surfaces became stiff and unresponsive. Japanese pilots who had survived encounters with P-40s described being unable to maneuver effectively during high-speed combat because their controls simply stopped responding properly. The Zero's ailerons and elevators used fabric covering stretched over metal frames. This construction was lighter and worked beautifully at normal combat speeds, but as velocity increased, the fabric would deform under aerodynamic pressure, and the control surfaces themselves would stiffen dramatically. Above approximately 350 miles per hour, many Zero pilots reported that their controls felt locked in place. The P-40's all-metal control surfaces didn't have this problem. Engine examination revealed another fundamental difference. The Allison V1710 was a liquid-cooled inline engine, far heavier than the Zero's radial, but offering different advantages and vulnerabilities. The engine block itself was robust and could sustain some battle damage. However, the cooling system presented a critical vulnerability. A single hit to the coolant lines or radiator could cause the engine to overheat and seize within minutes. Japanese engineers noted this weakness carefully. It was a trade-off inherent in liquid-cooled designs. Most significantly, the P-40 featured self-sealing fuel tanks and armor protection. Japanese engineers examined the fuel tank construction with growing concern. Rubber layers sandwiched between fuel tank walls would automatically seal bullet holes, preventing fuel loss and fire. The Zero had no such protection. A single incendiary round through a Zero fuel tank often meant catastrophic fire. The armor protection was equally impressive. A thick steel plate behind the pilot's seat could stop rifle-caliber rounds and shell fragments. The windscreen featured laminated bulletproof glass. Some engine-critical components had additional protective plating. The total weight penalty was substantial. Weight the Zero designers had eliminated to achieve their performance advantages. A Japanese test pilot who flew the captured P-40 provided his assessment in a report filed with Naval Air Headquarters. The aircraft feels heavy and requires more physical effort to maneuver compared to our Zero. I cannot turn with our fighters. However, I now understand why American pilots survive. This aircraft protects its pilot. The armor plating and self-sealing fuel tanks mean that hits which would eliminate our aircraft and pilot allow the P-40 to continue fighting or return to base. The American pilot can make mistakes and survive to learn from them. Our pilots must be perfect, or they perish. The armament installation offered another lesson. The P-40E carried 6 50-caliber Browning M2 machine guns, 3 in each wing, with approximately 235 rounds per gun. Total ammunition load exceeded 1,400 rounds. Fire duration at maximum rate was approximately 34 seconds of continuous firing. The Zero carried 2 7.7mm Type 97 machine guns with approximately 500 rounds each and 2 20mm Type 99 cannon with just 60 rounds per gun. Cannon fire duration was approximately 7 seconds before ammunition exhaustion. Japanese pilots had to be extraordinarily accurate because they had so little ammunition, particularly for their most powerful weapons. The 50-caliber Browning, while individually less destructive than a 20mm cannon shell, could be fired in sustained bursts. American pilots could make multiple firing passes, using their ammunition advantage to compensate for less precise shooting. The psychological effect was significant. Japanese pilots knew that when an American fighter got within range, it could fire continuously for extended periods, walking rounds onto target through sustained fire. The maintenance examination revealed American industrial philosophy. Every component was designed for field replacement with standard tools. Engine accessories were modular and accessible. Spark plugs could be reached without extensive disassembly. Oil filters could be changed quickly. Compare this to the Zero, which required more specialized procedures for many repairs. The P-40's Allison engine could be removed and replaced by trained ground crews using appropriate field equipment, though the time required varied considerably depending on conditions and available resources. A Zero engine change required specialized tools, factory-trained mechanics, and careful procedures. In sustained combat operations, the P-40's maintenance-friendly design meant American squadrons could potentially keep more aircraft operational, though both aircraft faced significant maintenance challenges in forward combat areas. Japanese engineers compiled their findings into a classified technical report dated October 1942. The conclusions were sobering. The American P-40 fighter represents a design philosophy fundamentally different from our own. Where we have pursued maximum performance through minimum weight, the Americans have accepted weight penalties to achieve structural strength, pilot protection, and sustained combat capability. The P-40 cannot outturn the Zero in traditional combat. However, it does not need to. American tactics exploit the P-40's advantages: superior diving speed, structural integrity at high velocity, and pilot survivability. Our pilots report that P-40 aircraft absorb damage that would eliminate our fighters and continue operating. American pilots who would be lost in our lightly built aircraft survive to fight again. This represents a strategic advantage we have not adequately considered. The report recommended immediate implementation of pilot armor and self-sealing fuel tanks in Japanese fighters. It noted that Japanese tactical doctrine, emphasizing turning combat, played directly into enemy hands by forcing engagements where the Zero's advantages could be exploited while negating the vulnerabilities that energy tactics would expose. It suggested that Japanese fighters should avoid combat with P-40s unless holding significant altitude advantage or numerical superiority. These recommendations were largely ignored. Japan's industrial capacity, already strained by expanding war commitments, couldn't support the modifications without reducing aircraft production. Adding armor and self-sealing tanks would increase Zero weight substantially, degrading the performance advantages that made it effective. Japanese tactical doctrine, refined through years of successful combat in China, was deeply ingrained and resistant to change. The human cost of this decision was documented in combat reports throughout 1943 and 1944. Japanese pilot casualties increased dramatically as American and Allied forces adopted energy tactics universally. The Flying Tiger's success had provided a blueprint that other P-40 units followed religiously. Never turn fight with Zeros, use altitude advantage to dive at high speed, make one firing pass, then zoom climb back to altitude using the P-40's superior dive speed and structural strength. Major General Claire Chennault, commander of the Flying Tigers and later the 14th Air Force in China, had developed these tactics through careful observation and analysis. His pilots received explicit instructions documented in training materials. The Zero can outturn you, outclimb you at low altitude, and out-accelerate you below 200 miles per hour. Therefore, never dogfight. Use your advantages: diving speed, level speed above 15,000 feet, and structural strength. Dive, shoot, climb away. Repeat until the enemy is destroyed or withdraws. These tactics worked because American pilots had the discipline to follow them and because the P-40's design made them possible. Japanese engineers examining the captured aircraft understood this completely. Their report noted, "American tactical doctrine matches aircraft capabilities precisely. They have accepted that their fighter cannot compete in traditional combat, so they have redefined fighter combat to exploit their strengths. This represents sophisticated military thinking that we must counter." But countering it required either building heavier fighters with better high-speed characteristics, which meant abandoning the Zero's advantages, or developing new tactics that negated American energy advantages. Neither option was readily achievable. Japanese fighter development programs were producing designs like the Kawasaki Ki-61 Tony and Nakajima Ki-84 Frank that incorporated some lessons from examining Allied fighters: heavier construction, better high-speed handling, improved protection. But these aircraft arrived late in the war and in insufficient numbers. The examination of the captured P-40 also revealed industrial capacity implications that were even more troubling than tactical concerns. The aircraft's data plate showed it was manufactured at Curtiss Wright's Buffalo, New York plant in March 1942. Production records that Japanese intelligence had compiled suggested that American factories were producing fighters at rates that exceeded Japan's entire aviation industry output. Japanese engineers calculated American production capacity based on intelligence reports and captured documentation. The numbers were staggering. Curtiss Wright alone would produce over 13,600 P-40s during the war. Combined with production by other American manufacturers of other fighter types, American fighter production exceeded Japan's capacity by margins that made long-term victory impossible. The maintenance logs from the captured P-40 told another story. The aircraft had logged 214 combat hours before being shot down. It had undergone multiple component replacements and sustained battle damage on several separate occasions that required field repairs. Yet it continued flying combat missions. This operational lifespan, while not extraordinary, demonstrated the aircraft's robust design. Many combat aircraft on both sides were lost long before accumulating such hours. The psychological impact on Japanese pilots who learned about the P-40's capabilities through intelligence briefings was significant. Many had been taught that the Zero's superiority was absolute, that American pilots survived only through luck or Japanese pilot error. Learning that the P-40 was deliberately designed to counter the Zero's advantages and that American tactics were specifically developed to exploit Japanese weaknesses was demoralizing. Saburo Sakai, one of Japan's highest-scoring aces with 64 confirmed victories, encountered P-40s repeatedly over New Guinea and the Solomons. In post-war interviews and writings, he reflected on the aircraft and the tactics American pilots used. He acknowledged that while the Zero could outmaneuver the P-40 in traditional dogfighting, American pilots simply refused to engage that way. Their diving attacks and immediate disengagement made them difficult targets, and the P-40's structural strength allowed them to execute these tactics safely at speeds where Zeros faced control difficulties. The Flying Tiger's record exemplified this effectiveness. Between December 1941 and July 1942, using tactics specifically designed around the P-40's strengths, they achieved one of the highest kill ratios in air combat history. Their success forced Japanese tactical revisions and inspired Allied fighter units throughout the Pacific and China-Burma-India theaters. In North Africa, P-40s flown by the Royal Air Force, South African Air Force, and United States Army Air Forces achieved similar success against German and Italian fighters. While the Messerschmitt Bf-109 was superior in many performance categories, P-40 pilots using energy tactics achieved competitive results. The Desert Air Force reported that P-40 Kitty Hawks, the British designation, were highly effective in the fighter-bomber role, combining adequate air combat capability with excellent ground attack effectiveness. The Soviet Union received approximately 2,300 P-40s through Lend-Lease. Soviet pilots initially disliked the aircraft, comparing it unfavorably to their own fighters, but units that adopted appropriate tactics found it effective, particularly in the ground attack role where its rugged construction and heavy armament proved valuable. By late 1943, Newer American fighters like the P-38 Lightning, P-47 Thunderbolt, and P-51 Mustang were supplanting the P-40 in frontline service. These aircraft incorporated lessons learned from P-40 operations while adding superior performance. But the P-40 continued serving effectively in secondary theaters and ground attack roles through war's end. Total P-40 production exceeded 13,600 aircraft, making it the third most produced American fighter of World War II. It served with the air forces of 28 nations. While never achieving the legendary status of the Mustang or the technological sophistication of the Lightning, the P-40 was arguably more important strategically because it was available in large numbers during the critical early war period when Allied forces desperately needed effective fighters. The Japanese engineers who examined the captured P-40 in New Guinea understood the tactical implications clearly, but the strategic realities were beyond their ability to address. Japan's industrial capacity, approximately one-tenth of American capacity, couldn't support the production and maintenance systems necessary to field fighters in American numbers. Japanese pilot training programs, disrupted by fuel shortages and accelerated by combat losses, couldn't produce pilots with the discipline and patience required for energy tactics. The final technical report on the captured P-40, completed in November 1942, concluded with a remarkably honest assessment. The American P-40 is not superior to the Zero in traditional performance metrics. However, it represents a superior approach to fighter design for sustained warfare. Its structural strength allows tactical flexibility our fighters lack. Its survivability features ensure pilot experience accumulates rather than being lost with each aircraft. Its design facilitates field maintenance despite combat damage. Most critically, it is produced in quantities we cannot match. We have built an excellent fighter for the war we expected. The Americans have built an adequate fighter for the war they are fighting. In sustained conflict, their approach will prevail. That prediction proved accurate. By 1944, Japanese air power was collapsing under the weight of accumulated losses, fuel shortages, and the inability to replace experienced pilots. American fighter forces, built around aircraft like the P-40 in the early war and increasingly equipped with superior later designs, achieved air superiority that Japan could never regain. The story of Japanese engineers examining the captured P-40 is ultimately about the difference between tactical excellence and strategic wisdom. Japan had built tactically superior fighters and trained tactically superior pilots for the kind of warfare they expected. But America had built fighters suited to their industrial capacity, developed tactics that exploited their aircraft's strengths while avoiding its weaknesses, and created training and logistics systems that could sustain operations indefinitely. The P-40 wasn't the best fighter of World War II by any traditional measure, but it was exactly the fighter America needed in 1941 and 1942. Available immediately, producible in quantity, robust enough to survive in combat, and capable enough to be effective when flown intelligently. That combination, more than any performance specification, explained why it kept beating the Zero despite the Japanese fighter's superior agility. Japanese engineers, who examined that captured aircraft in September 1942, learned a lesson their leadership never fully absorbed: that in modern industrial warfare, adequate equipment available in overwhelming numbers, supported by effective tactics and sustainable logistics, will defeat superior equipment that arrives in insufficient quantities. The P-40 taught that lesson repeatedly in skies from China to North Africa, from New Guinea to Burma. Japanese pilots paid for their nation's failure to learn it with their lives, while American pilots, in their heavy, unglamorous fighters, survived to fight another day, returned home, and eventually won the war,